Hello, Chem II, and welcome to the third video of Chapter 3. This one, we're going to focus a lot on mass-to-mass relationships within balanced chemical equations. So we've already talked about the mole in the first video. Then we started looking at the relationships between masses in a chemical formula, whether that be looking at the formula if it's an empirical formula or a molecular formula, but how the masses within the formula, how the masses of all the different elements relate in a formula. Now we're going to take it one step further and talk about mass relationships in reactions. So this section is section 3. And as I said in video 1, we're going to break section 3 actually into 5 separate videos. This is such an important concept in the Chemistry 2 classroom that we're going to break it into smaller chunks. First thing we're going to look at is mass-to-mass relationships and how they play a role in a reaction. So our goal today is to be able to relate masses of products and reactants to one another in a chemical reaction. So in a chemical reaction, in a balanced chemical equation, first things first, when you write a balanced chemical equation, the reactants will appear on the left-hand side of the reaction and the products will appear on the right-hand side. So if I were to have a reaction between, let's see if I can get my pen to work right, between sodium and chlorine, I would make sodium chloride. And that sodium chloride says that my reactants, my things I start with, are the sodium and the chlorine gas. Anything I'm going to end up with is the sodium chloride. And you always have a yield sign in the middle to indicate the direction from the beginning to the end. When you write a balanced equation, you always got to know what the reactants are and the products are in the reaction. And often, to do an experiment or analysis, you need to know what products there are of the reactions so you can properly balance the equation. So how do you write a chemical equation? Well, the first thing you do is write the skeletal equation, which means all the components not balanced in all. Now, this is the second piece is going to play a role off and on throughout the rest of this class, where sometimes it's going to be helpful or necessary to indicate the physical states of the products, whether they be solids or liquids or gases, or, as is going to be the case in the next chapter, all aqueous solutions dissolved in water. Then finally, what we're going to do is we're going to balance the equation using coefficients. And in Chem 1, you did this. You used the coefficients to determine the amount, the number of the different materials. So for instance, that sodium plus chlorine that we did a few seconds ago, in order to balance this, to make sure there's the same number of atoms on both sides, we're going to need 2 sodium atoms reacting with 1 chlorine atom, and we're going to make 2 sodium chloride formula units. So let's look at this. So here's an example. I have sodium hydroxide reacting with carbon dioxide that's in the air to form a colorless liquid, water, and a white powder, sodium carbonate. And then they just tell you as a sidebar, sodium carbonate sometimes added as a softening agent for water, so it makes your hard water soft. So first thing we need to do is translate all the names of the formulas and write a skeletal equation. And then also write the physical states of all the materials. Then balance by starting with an element that appears only at once on each side and balance it out. And ultimately, you're going to make sure that all the atoms of all the substances balance out on both sides. So we have sodium hydroxide, carbon dioxide reacting together to form, that's my arrow, water and sodium carbonate. Well, last chapter 3, you had a big chunk of it was being able to name and write the formulas correctly. So we're going to go ahead and write the formulas correctly. Skeletal equation would be that we have sodium hydroxide reacting with carbon dioxide to give you sodium carbonate and water. Now let's worry about the physical states. Sodium hydroxide is a solid, because they say a crystalline solid. Carbon dioxide, you should know, is a gas. And sodium carbonate is a solid. They said it was a precipitate. And water is a colorless liquid, which is water. Now we need to balance it. So in order to balance this, looks like over here, we have 2 sodiums, but over here we only have 1. So if we put a 2 here, then we have 2 sodiums. Let's see what else. We got 1 carbon on each side, so that's good. Let's see, now we have 2 hydrogens here and 2 over there. Let me check my oxygens. 2 here, plus another 2 here is 4. 3 here plus 1. I think I'm balanced. So putting that one single number out front balances this chemical equation. Let's make sure. So on the left side, I have 2 hydrogens. On the right side, I have 2. On the left side, I have 1 carbon. On the right side, I have 1. On the left side, now that I've balanced it, I have 2 sodiums, and on the right side also. And the oxygens, I have 4 on the left side and 4 on the right. So my balanced chemical equation turns out to be 2 molecules of sodium hydroxide need to react with 1 molecule of carbon dioxide to create 1 molecule of sodium carbonate and 1 molecule of water. The coefficients in the balanced chemical equation are going to represent the moles. It's going to represent the moles. So what this means is if I had this equation here, which has a lot weirder numbers, for every 2 moles of N2H4, I need 1 mole of N2O4. For every 2 moles of N2O4, I have N2H4, I need 3 moles. So what I have is a whole bunch of ratios of moles. In the first video in chapter 3, we got to this point where we were making these connections. And I just addressed in a balanced chemical equation, the coefficients, they are going to be mole-to-mole ratios, but they're also going to be particle-to-particle ratio and volume-to-volume ratios because they tell you how many relative to particles, molecules, formula units, whatever, relative to moles and relative to volumes, if they're at the same temperature and pressure, they're going to be ratios. So I just have developed a middle ground, a middle of this table. So let's think about this. I'm going to give you an example that's going to gradually grow into something a little more complicated, I want to say. So in a combustion of octane, how many moles of oxygen are needed to react with a certain number of moles of octane? Okay, so I want to know the mole-to-mole ratio. So I need first a balanced equation. My balanced equation is there, and it's not a pretty one. It's got really, really ugly coefficients. But I have my balanced equation, and I'm going to start with my 1.6 moles of octane, and that's that first compound, C8H18. So if I look at my coefficients in the equation between what I'm given and what I'm asked for, I'm given octane, and I'm asked for the amount of oxygen. So I need a 25-to-2 ratio. And that 25-to-2 ratio is going to be written in such a way that my coefficients, my units get to cancel. Notice that my moles of octane get to cancel. So if my moles of octane get to cancel, I can do the math, and I can find that I need 20.2 sig figs moles of oxygen in order to completely react with 1.6 moles of octane. So again, those coefficients from the balanced equation represent a mole-to-mole ratio. They also represent a volume-to-volume ratio. So if I had that same equation I had earlier, and I started off with 3.25 liters, and of the, let's see, that's hydrogen. Okay, so I'm looking at the ratio between what I'm being asked about, which is nitrogen, to what I am given, which is hydrogen. And I'm looking at that ratio, so it's a 3-to-1 ratio. Now the 3-to-1, instead of being a mole-to-mole ratio, is a volume-to-volume ratio, assuming both components, the nitrogen and hydrogen, are gases, and they are both at the same temperature and pressure. So I can do that math and find out that I have 1.08 liters of nitrogen. So what I've done here, and watch the magic here, is I've taken the chart, the mole diagram that we had in the first video, and I'm adding to it the one we just created that has the connectors that are the BCE, or the balanced chemical equation. BCE stands for balanced chemical equation. And if you look at this, what I've actually done is created a mirror image of the chart, where one side is talking about whatever compound, substance you're given information about, and then comparing it to a different compound, a different substance. That's where stoichiometry is pretty cool, that you're being asked for. You're being given information about one substance and you're being asked for some information about another substance. And you can meander all over this table. So far, when we were in the first chapter, we were going very readily between mass to mole, or mass to particles, or mass to volume, or moles. We were staying on the side, making these little jumps. Now we're going to jump across the pond and go over to the other side of the balance equation, or to another substance. It does not have to be a reactant compared to a product. It can be any two substances that are connected by a balanced chemical equation. So let's see how this works. So determine the mass of lithium hydroxide that is needed to produce 0.38 grams of lithium nitride. Sorry, determine the mass of lithium hydroxide that is produced, that's a product, that is created when I take 0.38 grams of lithium nitride and react it with an excess of water. What does this excess thing mean? That just means I have more than enough. Don't worry about it in the calculations. It means I have a ton of it. Don't worry about it. And honestly, if I'm going to think forward, in a later chapter, another 2 videos in the future, we're going to talk about what if we have the quantities of both things. What do we do there? But for right now, we're going to focus on one at a time. So we have our balance equation, and we don't, because the problem here is can't be balanced, because I have nitrogen on this side, but I don't have any nitrogens over here. So I'm going to help you out a little bit. The compound that is the other product happens to be ammonia. Okay. And if I balance this equation and do my little balancing act, I notice I have 3 lithiums over here, so I need 3 here. And do everything else, I find out that I need 3, 3, 1, and 1. So let's do this. So we need to go from grams of lithium nitride to grams of lithium hydroxide. And we're going to do that by using our mole diagram. So let's go back to the mole diagram. Here's the mole diagram. I'm given a mass. I'm given a mass. I'm asked for a mass of a different substance. I'm giving the lithium nitride mass, and I'm asked for the lithium hydroxide. Why did I put it in there? Lithium hydroxide mass. So I'm going to go mass to mole using my molar mass, mole to mole using my balance equation between lithium nitride and lithium hydroxide, and then go from mole to mass using my molar mass of my lithium hydroxide. I'm going to do it in a series of steps. So let's look at this. Let me go back to my original slide. So I have 0.38 grams of lithium nitride. I'm going to use my molar mass of lithium nitride to determine the number of moles. At this point, my grams will cancel. My grams will cancel, and I'm left with moles of lithium nitride. So I've gone from mass of lithium nitride to moles of lithium nitride. We said the next thing to do would be to go to moles of the unknown, which is the lithium hydroxide. We're going to do that by using the balance equation, looking at the comparison of the 3 to the 1. There's 3 hydroxides for every 1 lithium nitride. And then the last thing we said we need to do is use the molar mass of lithium hydroxide to go to the mass of lithium hydroxide. So we look that up, calculate it, do the math. Anything that's in the denominator, just divide by it. Anything that's in the numerator, multiply by it. Get an answer. Your final answer here is going to be, with sig figs, 0.78 grams. That means that if I started with 0.38 grams of lithium nitride and I reacted it with an excess of water and everything went perfectly, I could create 0.78 grams of lithium hydroxide. So that's the end of this video. I did one example here. We're going to do more in synchronous. We're going to do a lot more in synchronous, practicing a lot more. But this gives you the gist of how to go from mass to mole of the other thing to mass to mole to mass. So until next time, I will see you in synchronous, and toodles.